Okay, this is digital circuits. And we are on chapter 13. How did I spell chapter that way? Is that the French way? Looked un-American to me. Chapter 13, and we have two problems to do. E13.1 and E13.2 before we can get to chapter 14. Anybody know how far we have to go before we can call it okay for the semester?
That's up to you.
Yeah, all the way to December, of course. Yeah, okay, all right, exactly. Okay, so E13.1. Load 13.2a. Now, why would you want to load 13.2a for the first guy? It doesn't make any sense. Oh, that was bad. We only have version 10. E13.2a. All right. And this is a 4-bit shift register made with JK flip-flops. Press R to reset and press S to set. How many times must you press C to shift the 1 bit to the rightmost flip-flop? Okay, so this is one of those questions. Okay, so what do you say we turn it on first? So we turn it on. Okay, I'm going to shift R to reset. Where's the R? There's the R. Boom, boom. Okay, so R, you did see it move, right? Just barely. Okay, so R did that, and then we're going to hit set, S. Okay, and now I'm going to hit the C button, and I'm going to count how many times to get it from where it is there. I don't think the video shows my cursor, does it? I don't think it does. To the rightmost guy. Okay, so 1, 2, 3. All right. So back to here. E13.1a 3. Okay. What steps would you follow to shift an on bit into all 4 flip-flops? Okay, so I need a procedure. All right, so my procedure is going to hit R, hit S, hit C, hit S, hit C, hit S, hit C, hit S. I think that'll do it. What do you think that'll do it? Okay, that's my procedure. R, S, C, S, C, S, C, S. Okay, you got it memorized? All right, so R, S, C, S, C, S, C, S. Ta-da! The procedure works. Want me to do it again? No? Okay. Don't want me to do it again. Be that way. Because we do have a PDF file that we're generating. We should go and put that in it so that it's in the PDF file in case we want to look at it later. Okay, so next problem. E13. Now, why can't I make an E13.3? What's going on up here? Anybody know? E13.3. Okay, all set. Load the figure 13.5a. Okay. It didn't tell us to, but we're going to turn off this other guy first. All right. I'm going to load 13.5a. And this is a ring shift counter, so similar to some figure in the book. The word generator has high bits are used to inject into the low pulses at the set of the flip-flop. All right, whatever. All right. So obviously we have a word generator doing, this is a word generator, and it's doing something. So look at the binary thing, and it's hooked up to the 1 guy and the 15 guy, and the 15 guy is around here someplace. So they're either both 1 or they're both, or 1 and 0 and 0 and 0, and then I'm doing things here on the least significant bit. Okay, so I see that. And we're hooked up to the set and the reset. Okay, I see the most of the 15 and 14 is hooked up to set and reset, and the other guy is hooked up to the clock. All right, I got it all. Measure the time width of each positive output pulse. Okay, you ready? Boom. Okay, so we'll stop. Positive output pulse time width. So we'll move the cursor over to the beginning and to the end of one of the pulses, and they're all the same. Is that good enough? Yeah, that's probably good enough. And it tells me that the it's 1.05. No, the change 2.033. I bet you it's really supposed to be 2. What do you think? See if I can make it be 2. No, that's as close as I can get. So 2.033 milliseconds. A, T, the period. Now we're not going to use T, right? Because we use tau, the Greek letter, for something like that. So tau, 2.033 milliseconds, but we're sort of thinking it's really going to be 2. B, observe the output waveforms. Oh, I'm reading the wrong one. On a piece of paper, sketch what you think the outputs would look like if the clock pulse connection to the first to the last flip-flop was broken. Okay, so I'm looking at it. If the last one is broken, then it would never do anything. And if it never does anything, then the waveform would look like what? Okay, so I got it. I'm going to do what I think it looks like. Boom, 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 boom. Boom, 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 boom. Boom, boom, boom. Oh, that was really good. Second one. Third one. Oh, that's just so Marvy poo-poo. It's just totally amazing. Last one. Boom. So the far right guy is just a straight line low. All right, that's what we think. Now we're going to turn it on and try it. Well, we're going to disconnect something. What are we going to disconnect? This guy here? Oh, we're not going to disconnect anything unless we turn off the clock. Turn off the... How come you didn't turn off? Delete. Okay, very good. Now we're going to turn it on. Boom. What? Okay, what's wrong? We're going to have to get the this guy back up to the top. And now the word generator is back up to the top. Now we're going to turn it on. Boom. What is going on here? Set, reset, cycle. Well, all I had to do is just get to the top and tell it that's where I am. Set cursor. Alright, well, I'm set. You better do the right thing this time. Oh, there we go. Straight line. On the bottom. Other three guys are there. Ooh, I blew it. I'm wrong. What happened? What happened? What did I miss? Oh, the output Q and Q naught are fed back to the first one. So when this, that means I'm feeding back a 0, and it never happens again. All right, so I'm going to have to redo what I did. All right, so this guy goes away. This guy goes away. That guy goes away. That guy goes away. New answer. Flat line, flat line, flat line. Okay. Happy about that? Yeah, pretty much. Okay. So now we're going to go and proceed to chapter 14. And we'll, well, if we need the multi-sim program again, we'll just open it. And if we don't, then that'd be good too. So now we're in chapter 14. And we get to add to our vocabulary words again. We're going to have multivibrators. That's there. We're in polite company today? Okay, just checking out there. And, huh? That's a 4. Can't you tell? multivibrators. So multivibrators, what do you think they do? And, yeah, they probably do something like go up and down. Yeah, probably something like that. And 555 timers. What do you think 555 timers do? Time. Yeah, that'd be good. So a 555 timer might do that forever and ever, or it might do this only once. So it could be a one-shot, or it could be like a clock pulse, putting out a clock pulse. So it could do either one. Anyway, so those are the things that it does. Okay, so the first thing we have to look at is capacitors. And with little luck, you've already looked at capacitors in your circuit analysis class. I do believe so, right? No capacitors. Okay, so that means I can tell you whatever I want, and you'll have to believe it. Oh, yeah, this will be fun. Okay, so we have things. What do you think capacitors do? Capacitate, right. They hold charge until they give it up. Hold charge. Okay, well, that seems like a reasonable thing. What do batteries do? Batteries give you voltage. Do they give you charge? All right, so now we have to decide. Yeah, now we have to decide. Show of hands. Anybody know what voltage is? Okay, that's good. Voltage. Anybody know what current is? That's like the current news, like the current going down the river. Current. Current. So the issue is, what's charge? That's what you do with your bank account, with your charge card, right? Charge. So now we're into calculus, and we can say that current is the change in charge. Now, why did we use a Q for charge? I don't know. Change in time. So current at times t is going to be dq dt. Why did we go from a big case Q to a little case Q? I don't know. Seems like a reasonable thing to do. So now, what's Ohm's law? V is equal to IR. Okay, so that's good. IR. Excellent. So voltage across a resistor is V equal to IR. What do you think the voltage across the capacitor is? Ah. Yeah. It will be charge, divided by capacitance. So whatever the charge is on the capacitor divided by the capacitance will give you the voltage across the capacitor. Now, the charge is in coulombs. Coulombs. Okay? And the capacitance is in coulombs per volt. So if I take coulombs and divide it by coulombs per volt, I end up with volts. If I do a dimensional analysis, if I go coulombs. Now, why is C coulombs? Why can't C just be the speed of light like it's supposed to be? I don't know. Divided by C over V, then I can multiply by V over C, V over C, and these guys get crossed out, and those guys get crossed out, and they get crossed out, and all I have is voltage left. Okay, so you got that? All right, so you have coulombs at your charge. You have voltage across the capacitor, the number of coulombs you have divided by the capacitance in farads. Anybody spell farads for me? Here we go, farads. There we go, farads. There, I spelled it. There. Isn't that great? Okay, and then you got voltage across the resistor. Okay, so you got all those things in your mind, right? Yeah. All right, so now we got this. We got a battery here, and a battery has voltage, and we'll give it what do you think? 10 volts. 10 volts. Okay, and then we got a resistor, and then we got a capacitor. And we're not going to hook it up back there. And then we're going to go and put a switch in here. I got this switch. So it might be hooked up there. That was a dumb way to put in a switch. I'll put in the switch this way. Or it could be hooked up like that. So I could be down like that, or it could be over here. Okay. So I got a switch there. If my switch is hooked up like that, we say we are charging the capacitor. All right, now if I go and hook my switch down there, we say we are discharging the capacitor. Okay, so you got that? So I can charge the capacitor, I can discharge the capacitor. All right, now when I'm charging the capacitor, we have voltage across the resistor, and we have voltage across the capacitor. So when I'm charging the capacitor, okay, what is the voltage across the resistor plus the voltage across the capacitor? What is it equal to? 10 volts. Very good. Yes, 10 volts, exactly. So it's equal to 10 volts. All right, now, when I'm discharging the capacitor, if I could spell discharging, what is the voltage across the resistor plus the voltage across the capacitor? Now, what does Kirchhoff's law say about voltage? The sum of the voltages across the loop is going to be 0, right? So if I start here and I go that way and I come back to there, what should the sum of those two guys be? 0. Okay. So when I'm discharging, the voltage on the resistor is going to equal minus the voltage on the capacitor. Okay, so now we have charge, we have coulombs, we have farads, we've got discharging, we have charging. Okay, so we have all those things clear in our mind. Okay, and now we have Ohm's law, so we'll get a new piece of paper here. So I got this guy, and I've got some resistance, and I have some capacitance in farads, and my voltage across the resistor, Ohm's law says it's going to be IR, and the voltage across the capacitor, we said, was going to be charge divided by capacitance. Okay, and I'm charging, so that means that if this were 10 volts, then that has to equal to IR plus Q over C. Don't have much of a choice. Okay, and we said that the current is the change in charge, change in time, so we could write that as 10 volts is equal to R dq dt plus Q over C. Now, once we've done that, we have a differential equation. Once we have a differential equation and we have passed calculus 1 and 2 and differential equations, we can solve our differential equation, right? Yeah. So we can do it right now, because by the time you get done with Tech Math 4, you'll be able to do it anyway, so why not do it early? All right, so that seems reasonable. So I'm going to go, I don't particularly like the R here. So I'm going to rewrite this as 10. I'm going to rewrite it as E. Is E okay? Okay, so E over R is equal to dq dt plus Q over RC. Okay, that looks good. Now, in Chapter 1 of the differential equation, Chapter 1? Chapter 2. In Chapter 2 of the differential equation book, or Section 30.2 of the Tech Math book, we find that this thing has a characteristic equation. The characteristic equation is going to be M plus 1 over RC is equal to E over R. Okay, we find that that's the case. And but the characteristic equation of the homogeneous. Why isn't Jim here at times like this? You know, homogeneous. I can't spell it. A homogeneous equation. This would be 0. And therefore m is equal to minus 1 over RC. And the answer to this particular differential, the homogeneous differential equation, Q sub C, is going to be C1, which is a constant, e to the minus 1 over RC times T. Okay, so that's what we have. Now, we also have to find the particular solution because it isn't equal to 0. Okay, so we have a particular solution, and Q sub P, the particular solution, is going to be equal to some A, because all we have is a constant there, R, E over R. And so Q prime of the particular solution is going to be 0. And when we have 1 over RC of this guy, and we have one of those guys, we're going to get E over R. Okay, so that means that A over RC is equal to E over R, implying that A is equal to what? A is equal to EC. So if A were EC, then I'd have E over R. All right, so that being the case, the answer to my differential equation is that Q of T is going to be equal to some constant of integration, e to the minus 1 over RC T plus EC. Where this C is different from that C because this is something different. Okay, now we want to know what the current is at time t. So we don't know the current. So I of t, the current, is the derivative of Q with respect to t. So that's going to equal minus 1 over RC, C1, which is a constant of integration, e to the minus 1 over RCT. Okay, so now we know the current at times t, we know the charge on the capacitor at times t, and we're all set. Except we have some constant of integration there. We need some initial condition. So if our initial condition was that Q at 0 is 0, so I had some switch there, and the capacitor was empty when I started, then that means that I have to say that Q at 0 is supposed to be 0, so that means that C1 plus EC have to be 0, so C1 has to be equal minus EC, and now my equation becomes Q of T is equal to minus EC e to the minus 1 over RCT plus EC, and I can factor that and say, what can I say? 1 minus e to the minus 1 over RCT times EC. And that's my Q of T. With an initial condition that I'm equal to 0. All right, now let's see what the book has. Oh, look at that. They basically have the same thing. Isn't that cool? So equation 14.1, if I take the derivative and I look at the change in V, I get that blah, 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 blah. Okay, so Now that we've convinced ourselves that we haven't had Tech Math 4 yet, so we can't do that, we will accept the fact that on charge, we won't use that one. We'll use a different one. Oh, look at that! You have all those same equations all over again on the other page. Oh, I don't want to do any of those things. Okay, now we'll proceed down. What will the technician do? All right, you're a technician, right? So on charge, what happens? The capacitor charges. That's the voltage across the capacitor. On discharge, what happens? What happens? We discharge. That's what happens. Voltage across the capacitor, we go down. All right. On charge, well, let's not talk about that yet. Let's talk about time constant. Time constant. And we have this e to the minus t over rc. And we could write that as e to the minus t over the time constant. The time constant is RC. So in an RC circuit, the time constant's RC. Way to go, Doug. So the time constant is RC. If I am charging then after one time constant, I'm at 63% of fully charged. And after 5 time constants, I'm fully charged. If I could make a time constant sign there. 5 time constants, fully charged. I'm not really fully charged, but I'm going to just say I am. I'm like 99.99% fully charged. I can't even spell fully. So what happens is, after one time constant, I'm at 63% of the charge. Now at 2 time constants, where am I? I'm where I was, plus I'm 63% of the difference. All right, so we'll take out our calculator and say, okay, I got point. Turn it on. Turn on, stupid thing. All right, there we go. 0.36 plus. That was a minus sign. I'll do it again. 0.36 plus the difference plus parentheses 100 minus 0.36 close parentheses times 0.36. Boom. I fat fingered a key. I'll do it again. 0.36 plus parentheses 1 minus 0.36 close parentheses times 0.36. Boom. So now I'm at I had my pen overwrite. 0.86. I'm 86%. Of fully charged. I do 3 time constants. What am I going to do? I'm going to do 0.86 plus 0.36 times 1 minus 0.86. So I'm doing where I am plus 0.36, 63% of the difference to where I'm going, wherever it is I'm going. Okay, so I got that answer, but I'm not going to use 0.86. I'm going to use 0.8631. Okay, so I'm going to go plus 0.63 times, parentheses, 1 minus 0.8631, close parentheses, boom. So now I'm at, after 3 time constants, I'm at 94%, but I'm 94.9347. Okay, and then I do it again, and I say at 4 time constants, I'm at this guy, 0.94947 plus 0.63 of the difference, 1 minus 0.949347. Oh, isn't that great? I love the writing. Okay, plus 0.63 times, parentheses, 1 minus 0.949347. Boom. So now I'm at 98.125839%. And that's why we say after 5 time constants, we're going to be at 100% fully charged and we don't care anymore. Okay? Now, what happens on discharge? Right, so I'm doing discharge, boom, and I started at some point 100%, and after 1 time constant, well, if I charge 63%, then if I'm going to discharge, I'm going to be at 37%. So I'm going to be at 37% after 1 time constant. And then when I'm at 2 time constants, I'm going to be at 0.73 squared. That was dumb. 0.73 squared. So I'm going to be, after 2 time constants, I'm going to be at 13.69%. And then after 3 time constants times 0.37, I'm going to be at 5.0653%. And then after 4 time constants times 0.37, I'm going to be at 1.8.74%, if we could read that. And then when I get down to 5 time constants times 0.37, boom, I'm going to be at 0.69%. And that's why we say after 5 time constants, we're totally gone. It's out of there. We don't have to worry about it anymore. Okay, so that's all there is to know about that. There's other formulas in the book that you can use, but as technicians, you think about time constants. You think about 5 time constant is fully charged, fully discharged. The time constant is RC. When is it not RC? It is not RC if you have an inductor, L. All right, but digital circuit book, we don't have any L's. Not a problem. Circuit analysis book, you have inductors, L's. So you have to deal with time constants, but they're going to work the same way. The number's going to be different, but the inductor is going to charge, the inductor is going to discharge. The inductor, the capacitor is charging coulombs. The inductor is charging a magnetic field. Okay, so the magnetic field is building, the magnetic field is going away. It's not like I got a charge going on. Okay. And let's see, what else do we have to say? I guess that's good enough, right? Yeah. Yeah. You don't want to hear any more. Okay. Until Tech Math 4. Okay, so now we have a stable multivibrator. Oh, good. A stable. We got to get back to the things at hand here. A stable. That's sort of like you put a horse in it. BLE, a stable multivibrator. We've got a Schmitt trigger inverter here, and it is going to charge and then we have a capacitor and a resistor, and it's going to charge and discharge depending on what the inverter is doing, and because of the hysteresis of the inverter, it's going to go up and down, up and down, up and down. How is it going to start? Look at the circuit on page 685. What makes it start? Nothing, right? So you're going to have to kick start it, but once it's started, it'll keep on going forever. It's not going to be a problem. Maybe it'll build up a charge inside the chip itself to get started, and so that could happen. Okay, I turn the page, and I see this guy is going to charge, he's going to discharge, he's going to charge, he's going to discharge. And as he's doing that, he's making the Schmitt trigger turn on and turn off. Okay, so when he's turned on, I'm charging. When he's turned off, I'm discharging. And now I've got some waveform caused by that charging and discharging going on. I got some time high and I got some time low, and I have a whole lot of equations that I could use to figure them out. Do I really care about them? Maybe, but probably not. Only when I get to the problem set. All right, so now I've got a monostable. Mono, M-O-N-O, stable. So if an A stable only has one horse, what does a monostable have? Anyway, monostable multivibrator. Okay. Turn the page. Okay, so I'm going to use a RS flip-flop configuration, and I'm going to use a resistor and a capacitor, and I'm going to charge and I'm going to discharge, and I'm going to turn these guys on, and I'm going to turn them off, and I'm going to get a waveform that it's going to turn on, and then it's going to turn off. But I'm only going to have a small bit of the waveform come out. Oh well, that looks like fun. Turn the page. Integrated circuit monostable multivibrators. Okay, so I can buy one of these already put together for me, and it will go and do whatever it is that I want. And I can calculate the width of it, and I can calculate other things if I wanted to. I'll worry about those later. Turn the page again. And again, and again. Re-trigger, mono. Back to monostable. Mono means one, right? Mm-hmm. So it's only going to happen once. I'm going to get a pulse, period, the end. I've got to reset it if I want to see it again. The A-stable guy is going to go up, down, up, down, up, down, up, down, up, down, up, down for the rest of your life till it breaks. Page 695, we have a re-triggerable monostable. So now we got a trigger going in, triggering the multivibrator. Okay, isn't that lovely? Okay, so we can re-trigger it. We can have an output pulse. Page 698, we finally made it. The 555 timer, which can do everything. So I can configure this guy, and all he is just a mere 8-pin configuration, I think. Only 8 pins, and you're gonna do them in the lab too. The other guys you're not gonna do in the lab. Is it timer? TIMM? No, there's only one time. No one M in timer, right? Oh well, whatever. Try again. There we go, 555 timer. So I can configure this guy to be an A-stable multivibrator. I can configure him, turn the page, to be a, where is it? Turn it again. A monostable timer, so I can do that on page 709. And I can throw in a crystal so that he stays on the right frequency. And now my chapter is done. All right. So now it's time to talk about back to page 698, and we're worried about 555 timers. Okay. I see that I've got a ground pin. Isn't that lovely? I've got a trigger pin. Where's my trigger? Okay, I got a trigger pin. I got an output pin. I got a reset, and I got a control voltage. Turning the page. I've got a threshold, a discharge, and a voltage that I supply, anywhere from 4.5 to 18 volts. Okay, and I see that I have 2 comparator circuits. Comparator 1, comparator 2, and a set and a reset on an RS flip-flop. Okay, and then I got a reset for the RS flip-flop. And then I got a transistor sitting there going to ground if I need to. Okay, providing a path to ground. And then I got an RA and an RB, and depending on how big RA and RB will tell me whether or not what the pulse width is going to be. How long is it for it to be high? How long is the whole thing going to be? And I have formulas, page 700. Time low, 0.693 RBC. And then time, where's time high? Don't see it. Am I blind? Oh, there we go. Time high on page 702. 0.693 RA plus RBC. So I hook up a capacitor, I hook up 2 resistors, and I make it, I can calculate my time high, my time low. If I put them together, then that's going to be the total period, and life will be wonderful, and I won't possibly be able to remember those equations anyway. So the instructor is probably going to have to put them on the board for you if he's dumbass enough to ask you a question about it, right? Yeah, he's going to have to do that. And on page 699, there's 2 capacitors in that drawing. There's one on the left, and there's one a little bit more to the right than the left is, coming out of pin 5. What is that guy doing there, coming out of pin 5? He's keeping the whole thing stable. Why do we call it a 555 timer anyway? Somebody had 5 stuck someplace and couldn't do anything. It was before the Beatles wrote their song about number 9, and then if we would have done after that, then it would have been 999 timer. Is that what it is? Yeah, that's right. Ryan figured it out already. There's 3 resistors that are doing a voltage divider on VCC, and they're all 5K resistors. And that's why you would call it a 555 timer. So we're doing that voltage divider thingy, and then control comes out there, and going into the other guy goes there. Okay, so we have minus plus on our comparator. We have plus minus on our comparator, and then this guy comes out and is our trigger, and this guy comes out and he's our threshold. Now why does it have to both start with T? Why couldn't we call it something other than threshold? I didn't. I left out the S. Okay, there we go. And that's why it's called a 555 timer. We're doing a voltage divider, a VCC across the three resistors, and then we're throwing in external resistors, external capacitors to have charging and discharging paths which line us up to do what we need to do. So time low, 0.6, what is that? 0.693 RBC. Time high. High. 0.693 RA plus RB times C. And again, we're not going to remember those. And my period is going to be whatever the time low is plus the time high. Let me those two guys added together. .639. What does that look like? No. Oh, it's natural log of something. Natural log of 2. Natural log of 2. Where's my natural log button? Now, there it is. I found it. 2 natural log. Yeah, okay, so you could think of this, for those that, for the robotic kids, you'd want to think it as natural log 2 RBC and natural log 2 RA plus RB C. Oh, that looks terrible. Should I rewrite it? No. Okay, not gonna. Okay, no problem. And then for the monostable, what are we doing? We're going to do something different. We're going to put the VCC in a different spot. So if you look at the A-stable guy, we have a little bit different wiring. So the pin 4 and pin 8 both have VCC in both conditions, but now the trigger pin 2 in the monostable, the trigger and 6 have the same voltage. In the monostable, it's pin 6 and 7 with the same voltage. And now we got a different set of equations telling us how long the period is and how long time low and time high is and everything else. Okay, enough of that. Back to the problem set. Oh, we haven't started it yet. I remember. They have to be simple, right? 14.1, because your instructor has to be able to do them. 14.1. What type of multivibrator is also known as a one-shot, an RS flip-flop, and a free-running oscillator?
Mono?
All right, so A, one-shot. Monostable. Multivibrator. All right, B. RS flip-flop. Astable. Multivibrator. Free running. Astable. I don't recall ever putting that problem on a test. Next one. Hope they're getting harder. No, they better not. 14.3. 14.3. The capacitor in the figure above is initially discharged. How long after the switch is moved from position 2 to position 1 will it take the capacitor to reach 4 volts? Okay, so I'm going to do it as a technician. I'm not going to do it the way the book tells me. Too hard. So the time constant is RC, also known as 1000 K ohms times 470 picofarads. Well, not very much. Okay, so 100 W3 times 470 W minus 12. So I got 47 microseconds. Okay, so my time constant is 47 microseconds. And now I'm going to say to myself, okay, what am I going to? I'm going to 5 volts, and I want to know how long it takes me to get to 4 volts. Okay, so after 1 time constant, I'm going to be at 63% of the 5 volts. Okay, so 0.63 times 5. Boom. I'm going to be at 3.15 volts. Okay, at 2 time constants, I'm going to be at 3.15 volts plus 63% of the difference, 5 minus 3.15. All right, so plus 0.63 times parentheses 5 minus 3.15 close parentheses equals. Okay, so I'm going to be at 4.3155 volts. So, as a technician, my answer is going to be before 2 time constants. So it's going to be before 94 microseconds. Now, I can solve this with a differential equation and get it down to a gnat's ass, right? But I'm not going to do that. All I'm going to do is say it's going to be pretty close to 2 time constants. Is that the end of that problem? Yes, it is. 14.7. 14.7. Why is a Schmitt trigger inverter used for the astable circuit in the figure instead of a regular inverter like the 74HC40? Okay, this is a one-word answer. Would somebody care to give me that one word? No, it's not toggle. It is hysteresis. The whole reason it works is because of hysteresis. If we used an inverter that went up and down right at 0, there wouldn't be anything going on. But because of the hysteresis in the Schmitt trigger inverter, I'm going to see a stable multivibrator. So now the issue is, can I spell hysteresis? H-Y-S, T-E-R-S-I-S. Fine, close enough. Close enough. 1414. Might as well not even change the page here. 1414. Using the timing chart in figure 1418 for the 74123 chip, determine a good value for the resistance external and the capacitance external if we want the pulse width to be 400 nanoseconds. All right, well, we got to find figure 1418. Ooh, I found it, page 696, and I want to have output to be 400. So there's the 400 line, and I see that it crosses a thing there where R is 50K. So I'm going to use R as 50K. And I come down that piece of thingy there, and I see that it's at that line. So what is that? 2, 3, 4, 5. So it'd be at 5 picofarads. 5 picofarads. So if I built this circuit with an external resistance of 50 kilo ohms and a external capacitor of 5 picoseconds, I should have a bandwidth of 400 nanoseconds. Excellent. That means that we made it all the way to the E problems. No, we didn't. We have to do E16 yet. 1416. Okay, I'm looking at 1416. Sketch and label the waveform of V out of the 555 circuit in the figure below with the potentiometer set at 0 ohms. Okay, so I see 14-16. Okay, so I see a resistor, I see a resistor, I see a capacitor. I remember that this guy here is RA, and this guy here is RB, and that this guy here is C. I remember that I have 6.8K, and I got 4.7K, and I've got 100 pico, which would be 1 nano. Why wouldn't they just call it 1 nanofarad? That makes so much more sense. Okay, so that's what I have. And because we just went over the material, I know the time low is the square root of 2 RAC. And the time high, or is it the other way around, is the square root of 2 RA plus RB C. Now, I may have forgotten those formulas, so I'm going to go look them up because I'm that type of guy. Or somebody's going to tell me that I'm right, either way. Low. And I'm wrong. Typical. Typical, wrong already. So it's RB, see, for the time low. Okay, so that being the case, that's the math I want to do. So I'm low, square root of 2, Make sure RA and RB are in the right spot. Yes, they are. Okay, good. So, not the square root of 2, the natural log of 2. Who's going to correct that on me anyway? Somebody in the front row should have yelled and screamed about that already. Natural log 2. Natural log 2. Okay, so natural log 2 times RB, 4.7 double E3 times 1,000 pico, that's minus 12. Okay, so I'm going to be 3.26 microseconds. Okay, and time high square natural log of 2 times 11.5 double E3 times 1,000 pico double E minus 12, 7.97 microseconds. All right, let's clean that up just a little bit. Not much, just a little bit. Now, I'm supposed to make a graph. Okay, so this is voltage out. All right, and I'm going to be low, and then I'm going to be high, and then I'm going to be low, and then I'm going to be high, and then I'm going to be low, oh, and then I'm going to be high, and I'm going to be low again. Good enough? No? Okay, don't like that? Then right here to there is 7.47 microseconds, and from there to there is 3.26 microseconds. There we go, all done. Okay, now can we do the last two? You mean the things you can't read because they're so fouled up? Is that better? Yeah, that's all you need? All right. So we're back to what we're doing. What were we doing? Anybody know? 14. Are we in 14 or 15? We're in 14. All right, so I got an E problem to do. 14E4. E14.4. Turn the page quick. Do I have more than one? I only have one. So should I do it or should I wait until next week?
It's like the only thing we have to do next week on the schedule.
I know, it's the only thing we have to do, period. So might as well do it today.
Yeah.
And then we'll make Tuesday of next week a lab day. And then I won't have to hang out here. Okay, E14.4. Good plan. So if anybody comes to class on Tuesday, we expect you to be, when you all come to class on Tuesday, we expect you to go in the lab and start finishing off your labs because we know you're behind. Yeah, all of you. Yeah, you're only 3 labs behind? Typical. Okay, so.
We're pacing ourselves.
Yeah, you're waiting for Jim to do it, I know. 14. Which one am I doing anyway? E14.4. I need 14.8A. Okay, so I found it. Oh, that's very nice, yeah. Okay, 14.8A. Measure the time high, measure the time low. Boom. Why would I want to do the math when I can just measure it? All right, so time high is close enough. Can't do it with that marker. I have to. There we go. That's close enough. Okay, so time high is 4.063 microseconds. Right there, 4.063. I don't know. Once I get written down what I'm doing, then I'll go back and look. 14 for A. I want time high. 7.063. 7.063 microseconds. And then I want time low. And well, we already know we can't use that and make it work, so. Notice that when I'm right on the gnat's ass thing, it changes color. Isn't that cool? And here it won't do it. Okay, that's good. 4.735. 4.735 microseconds. A. B. Changing VCC to 9 volts makes these guys increase, decrease, or stay the same. Increase, decrease, or stay the same. The equation for time high and time low only have the resistance and the capacitance in it. How can I change the voltage and have it do squat? Right? So it better stay the same. Remain the same. Now that's counterintuitive. All right. Should we look at it and see?
We're doing 14.7 or 14.8?
14.3, 14.4. Well, 14.4. If you had your book open, which you didn't bring to class, you would notice that it says to load file 1418A to do problem 14.4.
Come on, E.
Yes.
Yeah.
So to do problem E14.4, we have to load section 14.8A. So perfectly okay. Okay, what were we doing anyway? We're going to go and change the voltage and see if it made any difference at all. All right, so we're going to turn it off, change the voltage to 9, turn it back on. Well, it's higher. Looks like the exact same number to me, 4.735, right? So when a capacitor is charging and discharging, it's a percentage of the difference that it's changing, right? So it could be going to 100,000 million, or it could be going to 2. It wouldn't matter. It'd take the same amount of time to get there. Okay. Changing RA to 10K makes time low increase, decrease, or remain the same. Well, as we recall, time low has RB in it, right? So if I change RA, time low remains the same. Okay, so I'm going to go remain same. C, remain same. And now we're going to go and change it. What are we changing? RA. I'm going to change RA to 10K. Okay. Change it to 10K. Turn on the circuit. Boom. And move our guys over. exactly the same, 4.731. So nothing changed. Okay.
Why does it start out like wired with this?
Because it was probably, that's a simulation thing. We're not, see the reset guy?
The red one?
Yeah, so it's a matter of when does it start. Okay, so don't be confused by that.
And this is the second portion.
Yeah.
Which is the rest of the
Yeah.
first division.
So there's some time that the internal circuit has to think that it wants to work. And it has to ask, questions like, do I like this guy that's turning me on? And did he date my sister? Things like that. And after it gets done through those initial checks to see whether or not he wants to play with you, then it'll start working. But in this particular case, it's a mathematical simulation that's doing it, not the chip's personality. Yeah. The chips have personalities? Oh, okay, well, I just wondered. Okay, last one. Changing the capacitance to 333 picofarads makes the frequency increase, decrease, remain the same. We were at 10,000. We're 1/3 as much, so it's going to go down. So it's going to decrease. Decrease. There we go. So now we're going to do it. See if it actually happens. There's the, oh, it's not at 1,000, it's at 6. It's still going to go down by half, though. I'm going to change this guy. 330. Okay, excellent. Turn it on. Boom. Bring up this. Notice that this time it's just a little bit. And now the frequency should be half. The time should be half. So we're at what we're at before anyway. I forget what it was. But whatever it is, should be less than that. And it is. You can see that it is smaller. 2.327. Okay, done with chapter 14. And of course we get to revisit it again in circuit analysis and revisit it again in our tech math sequence. Yeah. All right. Very good, guys. No class next week, Tuesday. Come in and do more lab. Unless you're listening to this video, and then you may have to be behind.